Thank you for joining this session on compressed air leak management. We're going to continue this conversation on compressed air conservation because it's an important one. I'm truly passionate about it, about this topic. I'm going to be joined this morning by a few fellow speakers. We'll have Christian Schreiber from Sonotech will give us a bit of an overview on how his ultrasonic technology works. We'll be followed by Brad Runda from Amcor, who will give us a bit of an overview of what they do over there and the procedures they utilize. And then, of course, Ken and Bill from the union, giving us a perspective on how they inspire the teams and companies to be conservative on how they use compressed air and fix leaks. So I'm Brad Taylor. I'm technical manager at NewTech Compressors. I've got 22 years technically in the industry. The fact is I've been doing this since I've been in diapers, I joke. Got memories of my father bringing little compressors home from work, climbing up on the workbench, playing with them. So that led to my experiences in building piston, rotary compressors. It really helped me understand the microsystems within a compressor, but then an expanded system within a customer's environment, such as this compressor network, these machines. It also led to doing my own analysis, data logging over the many years, and helped me understand the dynamics of the system, but more importantly, its leak rate. And some of the percentage numbers we hear thrown around, they're real. And what I want to talk about today is what that cost is. So here's a typical system. We all recognize this. We all have some type of a compressor, some type of filtration, maybe wet and dry tanks in the compressor room, maybe a mass flow regulator exiting the compressor room, going out to a piping distribution network, feed down with some compressed air drops, maybe going through a FRL, filter regulator lubricator. And then we go through some type of coupler set, maybe a hose, maybe an institute fitting involved, and then we feed into the production equipment. Automation machines, grinders, sanders, impacts, drivers, torque wrenches, you name it. Each one of these areas has a potential for a leak. So what are some of the costs of the compressor system? We're all familiar with the compressor room, right? Capital cost of the compressor equipment. Maintenance, repairs, all those things were negotiated with on the customer side. And then there's the energy, the part that's hardly ever talked about. And then there's the plant side, okay? If the supply side should fail, we have those hidden costs. Rejected parts, maybe damaged equipment if a pneumatic clamp is not holding at the proper force, maybe tool breakage. Scrap rates, these are all real cost scenarios of a compressor system. But we focus so much as compressors providers on the capital side, right? We're a compressor company, that's what we do. We sell compressors and maintain them. But the real cost, we've all seen some rendition of this chart. So I'm showing 80% of the energy cost. I'm going to show 73, right? 25% of that, about $5,000 a year in leakage on a 100 horsepower system running at a 75% load. But I want to encourage you, compressor service providers, make this another revenue stream for your company. Focus as much on the compressor room as you should be focusing on the plant side. Okay, there's a lot of opportunity, maybe even more opportunity. We can even recover 50% of that 25% leakage. That's probably more than some of our annual PMs in some instances. This is the chart I was referring to. 10% of a system, 10% leakage of a system is fairly typical. 20 to 10% is considered a tight system. I've seen as low as 2 or 3%, but those cases usually have maybe 5 or 10 production machines, very easy to manage. And more typically, we see between 20 and 30%. And the Department of Energy says that 25% is the average. But often we see north of 50%. They're usually larger facilities. They have hundreds of horsepower, and they won't provide us the downtime to fix those needs. So just some critical thinking here. Our parents drilled into us when we leave that front door open. Shut that front door, son, right? Mom would repeat it because we didn't do it. We don't do it. As parents now, we don't do it, right? Because we're paying the bill. Do you let your faucet drip? Maybe us guys do that don't stay home during the day. But our girlfriend or wife, they remind us, right? That annoying drip and that faucet in the bathroom. Fix it, will you? It's because that's annoying. Well, what if we could think of compressed air leaks on our production machines in the same way? Those users that have to hear that leakage throughout the day. It's annoying. It could be affecting their hearing. Make it personal, as we heard yesterday. We leave the lights on. You leave your car running when you get home. Often you see compressors running and there's no production in the shop. Okay, a lot of this is about awareness, about training, helping people understand. But I think we would really understand or take more action if we understood the true cost of compressed air, right? We see a lot of fancy formulas out there. My goal today is to try and simplify this so you can take it back to your staff, your engineers, more importantly, your customers, and help them understand the true cost of compressed air. So these 5 points I'm going to try and cover off in the next 20 minutes. Okay, understanding the cost, identifying leak points and tabulation methods, leak finding tools and some of the methods for using them, and then selling leak repair to management, and then maintaining the gain. Very simple formula. KGI gives us those efficiency numbers. Okay, varies by horsepower, as we know. Kilowatts per 100 CFM. Multiply that times the number of hours that operation or that compressor is running. That's how many hours the leaks are being fed. Multiply that times the rate that you're paying for electricity, including the associated taxes, right? Very, very simple formula. So in this case, we're going to use 2,000 hours, 8 cents, 22 kilowatts. Divide that by 100 to get kilowatts per 1 CFM. Multiply that by 2,000 hours for a single shift, times 8 cents. There's your number. $35.20 per CFM per shift. 2 shifts times 2. 3 shifts times 3. 24/7. Multiply it times 4.2. 24/7. That's about $150. A little bit less than $150 per 1 CFM. You're from California, paying 16 to 20 cents. Multiply that times 2. It just got real. I believe, when I go and do a lot of my visits with my customers out in the field, I refer to that number, and they're shocked. But it gives them an easy, especially maintenance, gives them a very easy value to make the quick decisions on whether they should repair a leak or not. That leaky coupler, you can hear it walking by in a semi-noisy factory. It's probably about 1 CFM leaking. Coupler sets are what, $8, $10? 3-month ROI, 1 week ROI for a 24/7 outfit. Not too bad, right? So let's talk about leak points. Many of these you guys I'm sure are aware of. In the compressor room, I came across a couple of these by chance. So many of you, maybe all of us here have been in the compressor industry for a while. Maybe have been a technician yourself. We know what that sump blow-down valve is, right? The little shuttle valve that blows down the sump to our 35 psi. There's typically two seals inside there. One is for your signal shift to allow the spool valve to shift inside of the cylinder. It's got an O-ring on it. I ran across it once when a compressor was loaded, and that seal was leaking past that. The compressed air was leaking past that seal. So that's expensive compressed air just being dumped right back into the inlet of your compressor, waiting to be recompressed. Same on the other side of that spool valve, where the seal is created to prevent the leakage or the blow-down air from the sump going to the inlet valve. Usually it's Teflon, sometimes it's rubber. I've also seen those corroded and leaking. Again, being dumped right back into the compression chamber to be recompressed. What about our inlet valves, right? Those normally closed inlet valves that require pressure to be opened. Again, a lot of those have that very expensive O-ring. That $1 O-ring that compressed air is seeping by during our compression cycle, all to be recompressed. So be on the lookout. Sometimes you can't hear that stuff because they're dumping it back into the inlet filter to be muffled. Make it part of your annual PMs if you're not doing your triennials, or if an O-ring should fail before the triennial. Okay? Drain valves, that's an obvious one. Jammed, leaky plunger valves, ball valves. Piping network, I don't know what you guys see, but I don't see a lot of leakage in my network unless I'm a stamping outfit that I've hard piped all my machines directly to the header. But typically, especially a larger system that the piping is all welded, you typically don't see a lot of leakage there. Maybe not much more than 1% anyways. And it's usually the challenge when there is a leak there, that's usually the most challenging to repair, okay, especially those black pipe systems. More so when you get above 2 inch. Then we've heard this term, the dirty 30, okay, that final connection to our production equipment. After that ball valve, after the drop. We've learned about dust collectors. People need to be trained. How do I know when this dust collector is failing or when these pulse valves are failing? Cylinder blow-down valves, very much like that sump blow-down valve that I was telling you about earlier. They work in a very similar fashion. When that cylinder is pressurized, there should not be any air coming out of the vent muffler. Hoses and couplers, the most common one. I brought a couple examples with me today. Most commonly on hand tools, you see a lot of leakage between the coupler and its mating surface. Now what happens is that the male portion of the coupler is usually directly screwed right into the air tool. What happens during that process is that as the tool is being worked, it's constantly working the coupler. It's working the material that starts to get sloppy, and the O-ring wears extremely quickly inside here. Okay, you're better off to provide some type of a leader on the tool. Put your coupler at the bottom, okay, so that all the action happens on the rubber hose, not in the coupler. Okay? When we're talking about couplers, I think I might mention a little bit further on, but connecting to production machines. Instead of using a coupler set, use some type of a high quality hose. My personal favorite is push lock, okay? Because the barb itself is a union within the tube, okay? Eaton, Parker are a couple of my favorites. I'm sure there's a lot more. But it eliminates pressure drop and it eliminates a leak point within that connection. Insta-tube fittings, that's another very common one, especially if the guy forgets to round the edge after he cuts it with a side cutter. Right? Leaves a burr on the edge. As soon as he pushes it in, he's just nicked it over and you get a leak point. So those are just a couple examples of where we see a majority of our leakage. Of course, in our production machines, cup seals, packing spool valves, motor vanes within an air tool that it's not working efficiently. That's leakage internal of the tool itself. Okay? This is probably the most difficult area in our production machines to get those repairs completed because of downtime. And then open blowing nozzles, right? Might call that artificial demand, but I would argue if it's sitting there blowing when no one's running that machine, it's a leak. We can debate that later. So here's a typical challenge. Okay, this is a real scenario. We're going to make this work. Look at all those tubes feeding in that particular section of this automation machine. Okay, several stations going around. This is a high production, high GP machine for this company. Getting downtime is next to impossible. What our job is to do is to help them understand the cost of the leakage within that machine. They know what the GP production is of that machine, right? But by having those two values, they now can make a calculated decision as to whether they should allow downtime or not. In some instances they can. Okay, the leakage, they just accept the leak rate and the cost of paying the energy to do it, it's acceptable. Because the downtime or the lost production far outweighs that value. Now, this is one of my favorites, one of my childhood memories. I don't know if you guys got into Lego Technic sets when you were growing up, but I sure did. Father bought me something similar to this. This was a pneumatic system. It's not nearly as fun as this. Sorry. A lot of memories. So in last year's session, I actually created a hashtag and this hasn't really taken off, but ban the coupler, okay? So this is a typical scenario of some type of a CNC production machine. But you can see they got coupler 1, there's probably a coupler feeding this hose on the other end. You get coupler 1, 2 couplers feeding 2 separate manifolds for whatever reason. Coupler 3, and for all I know that goes down and feeds another coupler on, who knows, the production machine, blow gun, torque wrench, whatever. Why? You guys be looking for this out of your customer sites, you'll become a hero. Take another look at this one. This one's worse. Okay? You can't see it. I'll show it in another slide, but there's actually 2 couplers up there, right? Got a coupler coming through. We go through a splitter so we can get 3 additional couplers. Come down to a FRL, got a coupler set there. Another coupler set here. And there's actually a coupler going into the top of the machine. This is a $1 million, multi-million dollar inkjet printer. And they couldn't find someone to reliably install it. Now, if this was a CNC machine, okay, mill typically, where you got tool changers, you know, large pulse of air quickly, you guys will be a hero if you can walk in and ask this question: which machines do you have low pressure alarms on? Go to that machine, look at the couplers, remove them, ask them for a wrench while you're on site, remove those couplers for them. You'll probably be able to lower their plant pressure by 5 to 7 psi. Not only did you increase their production, you saved them energy as well. Here's the picture I was showing you. Crazy. All that had to be done was remove that coupler and thread it right in. See it all the time, every day. And largely because we're just not educated on the dynamics of compressed air in this house. So, tools and methods for finding leakage. We heard Leslie say yesterday, using our ears, it is by far the most useful tool, as long as you can hear. Walking through customers' plants, Even in noisy production environments, I bet you can find 80% of their leakage by just walking around without any fancy ultrasonic equipment. Okay, soapy water, I believe if you have to get to that level, you're probably finding the last 1% of your plant. Okay? There's a lot of low-hanging fruit out there in regards to opportunities to fix leaks. And of course, ultrasonic. I won't steal your thunder. And then centralized mass flow meters, which is one of my favorite ways for totalizing compressed air leakage. Of course, you can do pump up and leak down tests. It's great if you can get the customer to provide downtime for a Saturday where there's no production machine consuming air. Point of use flow meters. Of course, these are methods for summing up the leaks. Ultrasonic, if you can get CFM indicating, which is very helpful. And of course, centralized mass flow. So as mentioned, one of my favorite is using centralized mass flow meters. So imagine this, you're able to insert some type of a mass flow meter back at the compressor room. Now, what are the key points to doing this method is you need to have a constant pressure output of the compressor room. Okay, whether you're going through a mass flow regulator or have the ability to switch a compressor into modulation for that short period of time, or ideally they have variable speed drive, okay, so they have a constant pressure. When it's in load unload, what will happen is when it loads, it's putting a higher pressure in the plant, filling the receiver tanks, which is artificially distorting your numbers, right? So you need a constant pressure. Then go through the plant. One point on the mass flow meters, technology is advancing to the point now where we can monitor the stuff from our phones. Okay, they're sending the stuff to the clouds. There's database that we can access from our phones. Walk the plant, isolate each machine one at a time, putting that information into a spreadsheet. That gives you the totalized leak rate for that particular production machine. Okay. Once you've gone through everything, shut off those ball valves one at a time, separating, subtract the difference from measurement A from measurement B, press A from press B. You end up with the headers being pressurized, right? So that's the leak rate of your headers. Now you can use that formula that I gave you earlier on the cost of the CFM for each one of those machines. Come up with a total value of that leak rate for that particular production machine. And then apply the cost, estimate the cost to conduct that repair. And you end up with a very simple ROI for each one of your production machines to conduct those leaks. The other thing I like about this is that it's a zero-sum game, right? I have this, I know my full output, you can verify that with the mass flow meter, and I bring it all the way back to zero. It's a very, very accurate way of doing it. But it's not always possible to get that downtime, and not much of us like to go in plants on a Saturday or Sunday. I'm sure we've all seen data logging graphs similar to this. Some variation of red line's pressure, blue line is the CFM. This is on a Monday. You can see they're just coming back, starting first shift. About 140 CFM is your constant flow. We identify that as their leak rate, continuous flow, whatever other artificial demands may be going on. Then of course, production carries on through the day. And if we had showed the slide for Saturday, it matches this exact same number. Very interesting, another way of totalizing your compressed air flow using an amp probe or some other data logging device. So getting the team involved, education, of course, part of what we're after today. Internal incentives, not a big fan of cash, but how about a pizza party? For all those that are involved, all those that influence that number, right? Maintenance, purchasing, that particular guy that reported a leak on his production machine should be reported for those type of things. Mandatory KPIs. Well, it was interesting what Leslie said yesterday. You need to make these things personal. Make it come from the heart. Okay? by fixing this leak helps you do this, or prevents this, that curing example I gave earlier. Awareness, okay, equals graphs is numbers, what leaks are costing the company. Put on those lunchroom walls. And then of course involve you guys, the service providers. So we've all heard this term, you can't manage what you don't measure. We just add the word continuously. And it's largely around what the advancements we've seen today in IoT. Embrace it, guys. This is the new norm. And the stuff's only getting less expensive. And the value that is delivered out of it is incredible. But the simplest and easiest form is still a spreadsheet. Okay? I like Google Sheet because it's collaborative. You can involve many people on your team, maintenance especially. And you can form your KPIs from this, include the operations guide, finance. This is a simple spreadsheet example I use. I actually involved the customer, built this sheet for him. I would check in with him every couple of weeks just to make sure he was adding values, simple date, the asset, type of leak, approximate leak rate, simple calculation would show him what the annual leak rate was, materials needed, he would put in the cost, manager could see it, and a simple ROI number. If it was under a year, he went ahead and executed it. If it was over a year, he would get permission. Now the interesting thing about this is that all he had to do was record the percent load on his compressor using the controller. And from that, we were able to just create a very simple scale as to what that CFM leak rate of the system is. Very useful tool. Really enlightened the customer and help them understand. So you fixed up your whole system, all the leakage is down to that final 5% maybe. We need to make sure that we go and adjust our compressor controls. May end up with a fixed speed compressor with a delay off timer set to 1 hour that's sitting there running idle. Okay, so don't forget that. So some final thoughts. Day log the system annually as service providers. If you're a customer, you can do it more often. Be much better. Make a person in the department responsible for leak repair. Try and make it personal as discussed. Talk to your energy provider about incentives. This is probably one of the biggest takeaways for you guys. I've done this myself. Reach out to your local providers. Find out who the managing company is for the incentives. Okay? Typically the incentive, the power company does not manage their own incentives. Many do. And ask them if you can be involved in the incentive writing process. It will take some time, show up at all the round tables, and try and influence the incentives for the next year, program year, based on that values, these values that I've given you. Whether it's around leak repair, higher incentives for variable speed drives, mass flow regulators, whatever it may be, you guys can get involved. And then align with the service provider. This is from the customer's perspective. US service providers, make this another revenue stream for your company. Okay? We spend time focusing on the maintenance of the supply side. You could double that revenue if we get involved in the demand side as well. What I would say is you need to make a department that is specifically tasked with doing that procedure. Otherwise, you guys will end up focusing on what you favor most or know best. That's the end of my presentation. Thank you.